Hello physics students. In this video, you're going to be learning about Kirchhoffs rules, what they are and how to apply them. Now before I go into Kirchhoffs rules, I just want to give you a little heads up. This video is probably going to be a little bit on the longer side because I'm going to do a couple example problems, and particularly the second one is a little lengthy. The next thing I want to say before I jump into Kirchhoffs rules is that you actually know them, and I'll explain how you know them after I go over the rules. So first thing, there are two of them. One is called the loop rule, and what the loop rule says is that if you add up the voltages around any wire loop, you're going to get 0 for an answer. But in order to apply this rule, you have to know how to add up the voltages. So what I'm going to first say is how you sum up the voltages of a resistor. So I have here a resistor, and suppose the current is flowing from left to right. That means the left side of the resistor is at a higher voltage, because that would mean the electric field points this way and the positive charge would flow that way. So if, for whatever reason, and I'll explain why later, let's suppose you're summing up the voltage of this resistor and you're going this way through the resistor with the current. You are going from high voltage to low voltage, so the voltage of this resistor in your summation will have to be negative IR. If, however, you're summing the other way through the same resistor, you're summing from a low voltage to a high voltage. So when you factor in the voltage of this resistor going this way in this calculation, you have to put plus IR instead of minus IR. All right, so let me create a pause to allow you to catch up before I move on. The next thing, how about batteries? How do you sum up delta V of any battery in a wire circuit? Now the first thing I want to point out before I go into this summation is that a battery, I didn't mention this earlier, but it actually is a source of chemical reactions that push charge. I mentioned that, but I don't think I mentioned that a battery also has a resistance inside of it, because a battery has metal in it and that has resistance. No matter what you do, you cannot eliminate the resistance of a metal unless you make a superconductor. So a battery, you have to think of it as having what we call an EMF in circuits. EMF stands for electromotive force. That's like the chemical reactions pumping the charge. But there's also an internal resistance inside the battery. And we typically use a lowercase r symbol for the internal resistance of the battery. Let's suppose the battery is discharging. In other words, you hook it to a light bulb, or your cell phone is running throughout the day and it's getting like depleting the charge. That means the current is flowing out of the positive end and into the negative end. So the current's going like this. If I'm summing through a battery in this loop rule operation, then what I would do is count up all the voltages I encounter as I'm going through this way. Now I encounter so the delta V from here to here would be minus IR, because I'm going with the current through a resistor. I'm going from higher voltage to lower voltage. So that's the minus IR, the voltage of that resistor. Then I go from the negative terminal of the chemical reactions to the positive, so I go up in voltage plus EMF. So the delta V from one side of the battery is less than the delta V of the chemical reactions because of the internal resistance. We call that voltage from here to here the terminal voltage of the battery. When the battery is discharging, it's less than the full voltage of the battery when it's not discharging. Let's suppose I'm recharging a battery, like when you plug your cell phone in at night. What that means is you're forcing current opposite to the battery to reverse the chemical reactions. So let's suppose I'm summing up the voltages in the Kirchhoff loop rule problem, and I'm going through a battery this way, and it's charging up. So now the current's flowing this way, so I'm going from high voltage to low voltage, so from low voltage to high voltage. So the voltage through the resistor is plus IR instead of minus IR, because of again, the direction of the current has changed. And then I go from the negative terminal of the chemical reactions to the positive, so I go plus EMF. So the terminal voltage of the battery is now the chemical reaction voltage plus the voltage of the internal resistance. It's higher than the battery during discharging. So to charge it, you need more volts than the battery itself to force the current backwards. So that's how you sum up voltages. Now, I mentioned, let me create a pause to allow you to copy this down. Okay, so I mentioned that you already knew this rule. How? Well, in a series circuit, I mentioned that this voltage was these added together. If you use Kirchhoff's loop rule and you go around this loop, what I tell people is that you imagine yourself a little tiny ant with a little tiny voltmeter, and you're walking around this circuit, going around the loop, adding up the voltages. So if you walk through this battery, you're going from the negative side to the positive side, so you go plus the voltage of the battery. Then you go through these minus IR, minus IR, minus IR, because you're going in the direction of the current, so you're going from high to low volts. So we went around the circuit, we add up all the voltages, our answer should be 0. Well, look what happens when I move these 3 to the other side. I get the voltage rule for a series circuit. So this is already, as I said, you already knew that. So that's Kirchhoff's loop rule. Now, the second rule is what we call the junction rule. So let me make some room. Okay, so the junction rule says that in any junction, and what we mean by a wire junction is wherever wires join together, like if you twist them together or solder them together, then the junction rule says that the current going into that junction has to equal the current going out of the junction. So an example of that, let's suppose we have I1 going like this, and maybe I2 going like that, and then I3 going like this, and I4 going like this. So the junction rule applied here would say that the current going in, which is, oh, I wanted I4 going the other way. The current going in, these two, I1 plus I4, has to be equal to the current coming out, I2 plus I3. So, simple rule, the junction rule. Again, you already know this rule. How do you already know it? Well, remember in parallel circuits, I said, and I'll draw it this way, that the current coming out of the battery was equal to the current of these 3 resistors. And it was just kind of like common sense. Made sense I know you said like a parking lot and roads. Well, look here, we've got a junction. So the current coming out of the battery is what's going into the junction. What's coming out are the currents in the individual resistors. So we already knew the junction rule. All right, so now what I want to do, as I said, is a couple examples. So, let me create a pause to allow you to copy this down. Okay, moving on. Let's take a look at the examples. So let's see what I had set up here. Example 1. So what I did is I took one battery that's a 10-volt battery here with an internal resistance and an EMF, and another 4-volt battery here, internal resistance 0.5 ohms and EMF of 4. And I put them like fighting each other. So they're trying to push current this way and that way, and there's a 7 ohm resistor in between. So what I want to do is, all right, so I'll create a pause to allow you to copy this down. Okay, so the first thing that we're going to do to solve this for part A is we're going to use the loop rule first. So as I said, imagine yourself to be a little tiny thing like an ant. And you're going to start in a point like this, and you're going to sum up the voltages that you encounter as you go from this point around in the loop. But you need to know which way the direction the current is flowing. So obviously, the 10 volts is going to win this, right? So this is pushing current this way. This is pushing that. So we have more volts, more electromotive force. This way, it's going to go like this. So we know the current goes like that. Let's go around and follow the current in the same direction. We could go the opposite if we wanted to, but let's follow the current and sum up the voltages that we encounter. So we'll say that 0 equals the sum of the voltages around, oh, I guess I could put delta V, around the loop. So 0, the little ant, goes through this resistor in the direction of the current, and the voltage encountered is minus IR because we're going from high volts to low volts. The ant steps here with a little voltmeter and measures, so it's going to lower volts. It'll measure minus I, which we do not know, times 0.5 ohms. And then the ant keeps walking and encounters the chemical reactions, walks from the negative side of the chemical reactions to the positive. So it's going to go to a higher voltage, right? Higher 10 volts. Ant keeps walking, encounters this resistor, follows the current. So this is high voltage, this is low voltage, so it's going to go minus IR. We don't know what I is, so we'll just say minus 7 ohms like that, minus IR. And then the ant encounters the chemical reactions here. The ant steps from the positive side of the chemical reactions to the negative side, so it's going to go down 4 volts to the negative side of the battery. So minus 4 volts, oops. Then the ant comes through the resistor, the current's going this way, so it goes to lower volts from high to low, so it goes minus IR. And I guess I could do like this, minus I times 0.5 ohms. So if I combine the voltages, I get 0 equals 6 volts. And I have 0.5I, 7.5I, 8I, and that's all minus 8 ohms. So if I subtract 6 from both sides, divide by 8, I get that the current is 3/4 of an amp. Or you could put 7.75 if you want. All right, so there's the current. By the way, you probably could have solved this without Kirchhoff's loop rule. You could have just said, look, we got kind of like 6 volts going this way and 8 ohms and use Ohm's law. All right, you could probably do that. But technically, it's more correct to use Kirchhoff's loop rule. The terminal voltage of each battery. So let's say that this point is A and this point is B. So those are the 2 terminals of the battery, right? Because this whole thing is the battery. So we want to go through the battery. We want to let our little ant climb through it and measure the voltages it encounters from one terminal to the other. So we could say delta V, as it's climbing through here, is going to be, first it encounters the resistor, and it's going in the direction of the current. So it goes from high volts to low volts, minus IR. Minus I of 3/4 of an amp times the 0.5 ohms. And then it goes through the chemical reactions, negative to positive, so it goes up 10 volts. Our little ant with its little voltmeter. So this is negative 3/8. We add that to that, and we get 9 5/8 volts. So slightly less than the EMF of the battery, 10, because the battery's discharging. All right, so let me make some room. Of course, I'm going to have to erase our problem, but that's okay. Okay, so if you need a moment to catch up, I'll create a pause to allow you to copy this down. Okay, let's move on. So the next thing is the terminal voltage of the other battery, the 4-volt battery. And again, this is now a little awkward because I had to erase it, but this is what we saw. And let's suppose the ant is going to tally going this way, but the current is going this way. So the first thing the ant, the first thing the ant's going to encounter is this resistor. It's going uphill. This has got to be high volts. This is low volts, because that's the way the current goes, from high to low volts. So we go plus IR, plus 3/4 of an amp times 0.5 ohms. And then the ant walks from the negative side of chemical reactions to the positive side, so it goes up 4 volts. So this is, again, 3/8. added to 4 gives us 4 3/8 volts, higher than the 4 volts EMF when a battery recharges. So that's the terminal voltage. What was the next thing I had to calculate? The chemical energy absorbed by the 4-volt battery in 20 seconds. So that's part C. What you could do is start with power equals the energy over time. In other words, the energy is power times time. And the easiest way to get the power is IV, okay? Because we have the current, we have the voltage, so we could say that the energy, the work, is IV, the power, times the time. So plugging it all in together, we could say 3/4 of an amp times the voltage of the chemical reactions, which is 4 volts, not the terminal voltage, because that includes the heat generated in the resistor. We only want the energy going into the chemical reactions, which are 4 volts. IV in 20 seconds. So that comes out to be 60 joules. Okay? All right, so if you need a moment to catch up, I'll create a pause to allow you to copy that down. Moving on. So D, the last part of this problem, which was the heat energy in the 4-volt battery in 20 seconds. The heat energy is going to be produced by that resistor, not the chemical reactions. So once again, maybe we could use this work or energy as power times time. And maybe the easiest one for power would be I squared R times time, that expression for power. Plugging in our known values, the current is 3/4 of an amp. The resistor value of the internal resistance of battery, 0.5 ohms. And the time is 20 seconds. Punch that in on a calculator, and you will get, looks like 5.6 joules of heat produced in that resistor. All right, so if you need a moment to catch up, I'll create a pause to allow you to copy that down. All right, so that was example 1. Now, ready for example 2? This is the longer one. Now, while I'm setting up, let me just state that I don't know if this will be on the AP because it's so long, it doesn't fit into the 15-minute kind of arrangement that they have with these free response questions. Doesn't mean it's not important. You'd have to learn how to do it and solve this for college or beyond electrical engineering. So, you know, we'll do it just basically for, because it is important if you're going to eventually study circuits. So here's the example. So I picked the numbers, so I got to be careful here so that this is relatively easily, the numbers are easy to handle. So we've got 1 ohm internal resistance and a 12 volt like this. Okay, so determine all the currents in this circuit. So let me give you a moment to pause so you could copy this down. All right, so in order to figure this out, we've got to actually apply both of Kirchhoffs' rules, the loop rule and the junction rule. To apply the loop rule, we need to know the directions of the currents. But which way are these currents going to go? Well, it's pretty obvious that the 12 volt will dominate and it will produce a current going this way. But does that then force current to go like this? Or does the 3 volt force this way and they both go down like this? I don't know. Well, I do know because I solved it out. But if you were solving this, you wouldn't necessarily know. So what you do is you guess. And it's perfectly okay. You'll see later that it works out even though you guessed. The guess I'm going to make is that this current goes like this and this current goes like that. I2 and I3, okay? Again, perfectly fine. It seems reasonable. These batteries will go like this. But like I said, I guessed incorrectly on purpose. I know that one of these guesses is wrong. I just want to show you that even if you guess incorrectly at the start of the problem, it's okay. We'll see that later and we'll be able to correct for our incorrect guess. So the first thing we're going to do is apply the junction rule. Always do that one because it's nice and easy. So right here is a junction, and we could say I in equals I out. In other words, I1 plus I2 equals the current coming out I3. So what I'm going to do is box this right away as equation 1, because we have 3 unknowns in one equation, and when that happens, you probably already guessed you're going to have to make a system of equations with multiple unknowns. So what we're going to do is make 3 equations, in fact, with 3 unknowns. All right, so next thing, I'm going to use the loop rule twice. And in order to do that, I'm going to put a little ant starting over here at point A, and the ant's going to go around this loop and tally up the voltages that it encounters. So loop A to A. So the ant goes in the direction of the current through this resistor, high volts to low volts. And it's going to sum up all those voltages and get 0 as an answer. So it goes minus IR through the resistor in the direction of the current. I'm going to actually leave the units off here because then it's going to get pretty confusing with all the units. So why is it I1? Well, if I1 is going here, then I1 is going here and I1 is going here. So this is I1. And then we go from the negative side of the chemical reactions to the positive. So that means the little ant is going, stepping up 12 volts. Again, I'm leaving the units off. The ant then walks through this resistor in the direction of the current. It goes from high volts to low volts. The voltage is minus IR. So minus I1 times 5. And then we're going to go down this loop, and then we go through this resistor in the direction of the current. The voltage will be from high to low volts, because we're going in the direction of current, minus IR here, but we have a different current, I3, times 6 ohms. And then the ant completes the loop, and therefore that is a correct expression because of Kirchhoff's loop rule. So what I'm going to do now is rearrange this, and notice I have these two together to make minus 6I1. These two together. And then this is minus 6I3, and this is positive 12. One more thing, just to simplify things, make them a little easier, I'm going to divide both sides by 6. And so that'll leave me an equation of 2 minus I1 minus I3. Here's another equation. I'll call it E2, equation 2. 2 unknowns, so I can't solve that again. So what I need is I'm going to make a third equation. I'm going to take another ant, and I'm going to say, ant, you start on point B and sum around this loop all the voltages you encounter. So okay, so loop B to loop B. And so here we go. Let's go with the current. We're going to go minus IR through this resistor because the current's going this way. The ant's walking from high volts to low volts. So 0 will be minus IR. Actually, I'll put RI. 1 times I2 in that branch. Then the ant walks from the negative side of the chemical reactions to the positive. So it goes up 3 volts, plus 3. The ant keeps walking, goes from this side of the resistor to this side with his little voltmeter and measures negative IR, negative resistance times I2. Then the ant makes a detour down here, measures minus IR here, minus resistance times current, but I3 in this resistor. And then the ant's completed their loop, so the voltages added up equal 0. What I'm going to do is now combine these two and get minus 3i2. And then minus 6i3. And then plus 3. I'll divide both sides by 3, giving me 0 equals 3 over 3, or 1, minus I2 minus 2I3. And there's my third equation. So let me create a pause to allow you to copy this down. Okay, so now comes the tricky part for me, because I only have 2 chalkboards here available. I wish I had all 4, but then things would be too small on the video. So I'm going to have to erase this, and then we're going to have to talk about it later. Awkward. So unfortunately, I don't see any other way to do it. Okay. So what I'm going to do is, first thing that I'm going to do is, let's see, I'm going to take equation 1 right here and solve it for I1. So from equation 1, if I move I2 to this side, I have I1 equals I3 minus I2. Right? Why did I do that? Because I want to plug this in here and get rid of I1. Then what I'll have is 2 equations with 3 and 2 in them, which I could then solve. So basically what I'm getting at is you have to solve the system of equations. There's a lot of ways to do that. There's no one way. In fact, there's a way to do it with matrices, you may know, which you're welcome to do with a calculator. But I'm just going to show you how to solve it with brute substitutions. So this now goes into equation 2. 0 equals 2 minus I1, which is this. And then minus I3. So when I break up these parentheses or get rid of the parentheses, what I have is 2 still here, and then minus I3 and minus I3, or minus 2I3. Okay, so I2 will be this 2I3 minus 2. All right, that's I2, which goes into equation 3. So now equation 3 becomes 1 minus I2, which is this. Okay, that's I2. And then we have to still have this minus 2I3 over here. All right, now this is 0 equals 1 plus 2, which is 3, when this negative goes here. Then we have negative 2i3, or negative 4i3. Subtract the 3 to this side, divide both sides by negative 4, and you get I3 equals 3/4 of an amp. There, finally, got one of the currents. Now, once we have that, we can look for an equation we could plug that into to solve for another current. Like, for example, let me see, which, I got to look back at the picture. Let's go for I1. So that means with I3, I could find this using equation 2. So into equation 2, we could say 0 equals 2 minus I1 minus I3, which we figured out is 3/4 of an amp. So this is now going to be 1 1/4 or 5/4. And we could move the I1 to this side and get I1 equals 5/4 amps. Okay, so that is the second current. And then the last thing, we can solve for the current in resistor 2, I2, using equation 1, which was the junction rule. which was, I erased it, but let me look back. It was I1 plus I2 equals I3. So we could say I1 plus I2 equals I3. I'm going to write it down because I don't have it on my board anymore. So I1 is 5/4 of an amp. I2 is what we're looking for. And I3 was 3/4 of an amp. So what we do is we subtract 5/4 of an amp from both sides, and we get negative 2/4 amps on this side. In other words, negative 1/2 amp is I2. And there is the final current, okay? So again, remember all the way back in the beginning, I said, you don't know how to guess which way the currents go. Just guess anyway. If you guess incorrectly, you'll figure it out eventually. So let's go back to that diagram, the original diagram. Maybe I'll slip it in over here. And I won't draw the resistors. I'll just draw those boxes to save time. So what I said is that I1 went like this, I2 went like this, and I3 went like this. That was my guess. I can now see I was wrong with current 2 because it came out negative, which means that the current 2 actually goes like this. And guessing wrong was okay because the minus sign just tells me, hey, make it go the other way. That's the real way it goes. So that's the nice thing about Kirchhoffs rules guessing. The current comes out of here, forces this battery to recharge, and then goes down through this resistor because of that 12 volts over here. So that was a really kind of long, tedious Kirchhoffs loop and junction rule application. When you have 2 loops like this, batteries and resistors in 2 loops, you always get a system of equations in the problem. All right, so, but that was Kirchhoffs rules. Again, this probably won't come up on the AP. Focus in on the rules themselves, that the summing of the voltages around any circuit loop is 0, kind of like the series circuit voltage rule, or that at a junction, any current going into the wire junction has to equal the current going out, just like the I relationship in a parallel circuit. So I hope you enjoyed the video. I hope it wasn't too tedious. I'll see you in the next physics video.